So next, let's examine how an L system might be implemented in code, just to get a sense of the data that we have to work with and to start to get an intuition for how we might translate that data, right? Those strings that we're iterating over and building over time, and how we might translate that into something visual. So now all the procedural tasks that we're doing in 3D in this course will all be done in Maya. So I have implemented this L system in Maya using Python. Although for the time being, we aren't actually going to be generating any 3D objects. The result of this script will just be outputting strings to the console. So if I go ahead and run this, we can see that it does give me we just start by defining a user interface to work with, and we have a next generation button, which is going to run this next generation function, which we'll take a look at in just a second. But we can see that starting off with the axiom A, if I hit next generation a few times here, we can see that we're actually working with the same L system that we just drew out a few moments ago. So to take a look at how this L system is implemented, you can scroll down here and see that, well, first I've made a note of the alphabet that I'm working with, and that'll be just the characters A and B. Again, the starting axiom will just be the string A, and we have two rules. And we'll see in a second why I've implemented these as just a list of two strings, but basically the first element in the list is the character we're looking for, and the second element is the string that we're going to replace that character with. All right, so every time we hit that next generation button, we can see that the previously generated string or sentence is accepted as a parameter. We create a variable for temporarily keeping track of the new sentence that we're building. Then we iterate through all the characters of the incoming sentence and just checking them one by one. We just check if the character is the character defined in the first rule, right? So is it an A? If it is an A, then we simply concatenate on the result of rule 1, right? On the other hand, if the character we encountered was a B, then we concatenate on the associated, conversion, if you will, right? Of rule 2 in this case, right? So if it was a B, then we will be concatenating on an A, right, onto our working sentence. I do just print out the working sentence so that we can see it after every iteration, and then return the result so it is ready to be used for the next iteration. All right, so there's a very simple implementation for an L system, again using some very simple rules, but we can see that it's quite easy to do in code and quite easy to get our hands on these resulting strings. All right, so we've seen how to generate these evolving strings. So let's take a look at one way, at least, we could translate those strings into something visual. So I've loaded in another L system here, and this is actually based on the Cantor set, which is a fairly well-known L system. Again, we're using A and B as our alphabet. No constants, just the variables A and B. We are starting with the axiom A, and then our rules are slightly different here. A becomes ABA, B becomes BBB. So let's go ahead and run this and just create a few generations. So we can see that again we have a string that increases in length and complexity over time here. But what we can do now, if I just run this again and reset, we can actually interpret this sentence and create some 3D objects using the resulting string as a set of instructions. So actually, I'm just gonna start with our axiom, interpret that, and just frame the results here. So what I've decided to do for this implementation of a Cantor set is to interpret the character A as a large cube. So when we encounter an A, we create a large cube. All right, so I'm going to hit next generation here and create the string ABA. Then I'm going to go ahead and interpret this. And we'll see that that generates something that looks a little bit different here. So I'm choosing to interpret B's as small cubes. So by interpreting the string ABA, we get big, little, big, and well, so on and so forth, right? We can just maybe create another generation and then go ahead and interpret that. So here we get something a little bit more complex. Make a new generation and perhaps interpret that. All right, so we can increase complexity as much as we want, and when we interpret the results, we'll get something that hopefully looks quite interesting, right? So now this isn't mind-bogglingly interesting, right? Just interpreting characters as different types of objects. But you can already start to see, I mean, hey, maybe we are quickly trying to put together maybe a cityscape, and we're just trying to generate rows of buildings with, not quite random distributions of building types, for example, but maybe we want the distributions to be somewhat uniform. And in this case, this L system generates quite symmetrical distributions of objects, right? So if we needed to generate that symmetrical distribution, maybe an implementation even as simple as this might get the job done. All right, so this is one way of interpreting the sentences that we're generating with an L system.